welcome back to this NPTEL online certification course in molecular rearrangement and reactive intermediates. In the last couple of class, I was started talking about the organosulfur chemistry. Previously I talked about organosilicon chemistry, and in the today's class I am going to start with organophosphorus chemistry. So these are the three different p block elements we want to cover in this course. In the today's class, my focus to talk about the discovery of phosphorus and different type of organophosphorus compound, and then try to talk about some of the important reaction, like I think the Wittig reaction we are going to learn. It's a very important reaction for the synthesis of olefin. We talk about the different selectivity, modification of this reaction, the Horner's Wadsworth Emmons modification. Then there are several other modifications of this reaction. We are going to talk about that, Appel reaction, and finally finish with the Schrodinger reaction. So first thing is the discovery of the phosphorus. So Henning Brand in 1669, he was an alchemist. So he I think it's an accidentally discovery of phosphorus. He was searching for something else, and actually he found the phosphorus. Okay. So after, I think you can see the phosphorus actually is a group 15 element, and again period 3 is a p block element having this 3s2 3p3. This is the outer shell. It could be, so there are two different type of phosphorus. We're going to come back in a minute. One is the white, another is the red. Both having the different type of the boiling point. We're going to come back to their structures. We're going to talk about the oxidation state of the phosphorus starting from the 0 to, you will see, up to +5. And again the phosphorus are, it could be a trivalent or pentavalent. So we're going to see some of these different type of compounds. Again, I think phosphorus is present everywhere. I think inside the human body too. You can see there are flame retardants from fertilizers, and of course the vitamin B6, the pyridoxyl diphosphate. There are the RNase has this the phosphate. There are antibiotics, and of course there are a lot more about the drugs where the phosphorus is present. So marketed drugs, bioactive compounds, and then there are a lot of the phosphorus. Of course the agrochemical is the most of the important thing, the fertilizers, and then there are also phosphorus based reagent. And the other very important thing is phosphorus based ligands. If you see, the phosphine based ligands play a very important role for doing the different type of tungsten metal catalyst, and also even in tungsten metal free carbon-carbon bond forming reaction. I am going to talk about the different phosphorus compound. Here are the list of different trivalent phosphorus compound. The phosphine, once the phosphorus having 3H or 3-alkyl, aryl, or if you have a halides. So these are the class of the compound called phosphine. And then there are phosphinides. When one of the R is replaced by one oxygen here, this is called phosphinides. Then phosphonides, 2 R is replaced by 2 OR, this is called phosphonides. And then finally phosphite. Okay, when you will see that 3 of this R group was replaced by 3 OR group. So if you see also what you are seeing here, all the all of them are the important thing is, from going to here and there, you are giving more electron density into the phosphorus. Okay. So if you think about the nucleophilicity wise, this one, the phosphide will be more nucleophilic. And then we are going to talk about some of the tetravalent ones. So we talk about trivalent. Now we are going to talk about the tetravalent. Then the phosphonium salts. So if the phosphines, if react, phosphines are also can participate very nicely for the SN2 reaction with a alkyl iodide. What is going to happen? You end up getting to R3 R dash plus. So we call this phosphonium salts. Okay, we are going to talk about some of these also. And then from the phosphonium salt, which I discussed in the previous slide, if you give a base, so what I was telling, that if you have a phosphonium salt like this, CH2R, and you have R or R dash, let's write In the phosphonium salt, if you so this is a plus on the phosphorus. If you use a base, then this can able to abstract this proton to generate a minus. So that can form a double bond. We call them this compound as a ylite. You have learned that if there is a plus and minus. So this type of compound you can write them like this also, like a P double bond R. So we call them ylite, okay, phosphorus based ylites. Then there are compound like azaphosphine, where your oxygen will be replaced by a NR, okay, oxygen replaced by a nitrogen. Then phosphine oxides, okay, I think this is another very important compounds, and you will see a lot of the phosphorus chemistry, the byproduct will be phosphine oxide. Then phosphinates, okay, you can see another compounds, phosphonate having phosphorus with oxygen, and then there will be one of the R will be replaced by one of the OR group. So if you see from phosphine oxide, if you replace one R by one of the OR group, this is called a phosphonate. Then phosphonate, where you can see there oxygen is present here, but two of the R group replaced by OR group. When three of them will be replaced, you will see these are called phosphate, okay. Again, so you can see that here there are I think there are also phosphorus based acid like phosphoric acid, and also there are of course other different phosphorus compound, but most of them you will see in these two class, either it could be a trivalent or pentavalent, and with very less amount structure you will see which has tetravalent, like one we have already mentioned. So that's the structure. Now come to the oxidation state. Again the phosphorus having from 0 to +5, okay. So if you see the elemental phosphorus, elemental phosphorus having the 0 oxidation state, once you go to the the hypophosphorus acid, and then once you come to the phosphine, then you will see this is a +3 oxidation state, and once you come to phosphoric acid, and at the time you can see it is going to the +5 oxidation state, okay. So this actually varies, and you will see different oxidation, and we will see different type of reaction where you can able to convert a compound which are +3 oxidation state to +5 oxidation state of phosphorus, okay. So I am going to start with the very important reaction developed by Professor George Utic, and it was a Utic olefination reaction. So actually we talk about this ylite the one slide before that, you can able to make the phosphonium salt, correct. We talk about that if you have a compound called this phosphonium salt, so this is a phosphonium salt, and now if you use a base, this is going to generate this ylite. Now again in this ylite you will see the carbon having, so you can see this is a carbon ion and phosphorus with a positive charge. So that means this carbon ion now can able to react with aldehyde. We have already talked about a lot of the sulfur based ylite chemistry. I think you have seen that very similar type of reaction here. This carbon is going to attack to the corresponding aldehyde or ketone, and from there we are going to talk about the details mechanism, but at the end the triphenyl phosphine oxide is going to eliminate through formation of a 4-member ring. We end up getting to the corresponding olefin, okay. Again, as I was mentioning the first step, how do you synthesize this type of ylite? I think first step is the SN2 reaction, trialkyl phosphines, which are electron rich, very good nucleophile, going to participate in this reaction, in this SN2 reaction to form the phosphonium. Then you have to use a strong base to abstract this proton, correct, to generate the phosphorus ylite. Again, different type of base is used, potassium tiohydroxide, N-butyl lithium, correct. There are different base can be used to generate the phosphorus ylite. Once you have ylite, you can now add to the corresponding carbonyl compound, the ketone or aldehyde, which form the oxaphosphetine intermediate. So this is the one important intermediate which is going to form, okay. So now again I think the question comes, what type of oxaphosphetine they are going to form. They are going to form a 3O or erythro. So that again the very same problem we are going to talk about where you have seen in case of Peterson olefination, correct? Remember that when the nucleophile going to attack to the corresponding the carbonyl group, which phase it is going to attack, because it has to attack so that in the corresponding when after the attacking happens, the next step will be the formation of the oxaphosphatine intermediate. From there it is going to form the corresponding olefin. So we are going to learn in a minute, depending on which oxaphosphatine going to form, it is going to give you either E or Z olefin. So here you can see in this particular example, we can see clearly this. So we can see these ylides react with the corresponding aldehyde to form the Z olefin. But in case of the other cases where what we are seeing here, once you are generating a ylide, but you have the carbon ion which have a ester group. So if you try to compare this carbon ion A versus B, which one you think will be more stabilized? I am sure the B will be the more stabilized carbon ion because of the presence of the ester group. So here what we are seeing, once it is going to react with this aldehyde and form this corresponding olefin here, we are seeing the the 96% of the product, but E only product is forming. So one case we are seeing the Z product, one case we are seeing the E product formation happening. So we can say that A can be unstabilized, there is not stabilizing group, like not a electron withdrawing group except the triphenyl PPH3 plus, there is no other stabilizing group is there. But here you have a stabilizing group, so we can classify them stabilized versus non-stabilized or unstabilized. Again you can see what is happening here. We are seeing that if you have a stabilized ylide, it is going to give E product as a major, E olefin as a major product. If it is unstable ylide, it is going to give you the Z olefin as a major product. So now we are going to learn why that is happening, why the stabilizing ylide giving a different product compared to unstabilized ylide. What is the difference? Again the difference comes again very similar to the Peterson olefination, the first step of attacking. When the attacking is happening, there could be erythropoiesis. So there is two different reversible steps in this reaction. One is the first step of the formation of the attacking of this nucleophile to this aldehyde or ketone, and then the next thing is the next reversible thing is the oxaphosphatine intermediate formation. So there is two different reversible steps. Now depending on, so now the depending on the size and depending of this R2 R1 group, and also the most important thing, the depending on the stability of the ylide. Okay, these two reversible steps can be controlled. But once it will go to the oxaphosphatine intermediate, it will go to the irreversible step, which is going to give you the corresponding Z or E olefin. So here here what we are seeing, if it is an unstable ylide, you can see this is not a stabilized one, so it is going to react fast. So this is a very fast step. Once it is going to react fast, so the kinetics is going to take the major role here. It is going to go for formation of the cis oxaphosphatine intermediate through this equilibrium. It is going to, because this is a fast attacking happening, so this is going to form the cis oxaphosphatine very fast, and then from there it is going to go for, so you can see there is a formation of this phosphorus oxygen bond and then carbon carbon double bond. So this is going to get collapsed, and then it is going to end up formation of the Z olefin. Okay. So again you can see in these cases the kinetics is going to take care. So that's why you can see we are going to form the corresponding Z olefin through this, because this is going to be a scene of elimination, because these two phosphorus and the oxygen are going to come from the same site. They form triphenyl phosphine oxide or trialkyl phosphine oxide, and then this is going to come out and going to form the corresponding olefin, corresponding Z olefin. Now question comes, what is happening if you have a stabilized one? Now if you have a stabilized one, now the important thing becomes that there is two possibility, because now once it is going to attack here, now that first thing is, once the attacking is happening here, as the corresponding carbon ion is stabilized one, so this is becoming a rate determining step, and there is a two possibility. Now a formation of the oxaphosphatine intermediate, it could be it try to form one of the oxaphosphatine which will be more stable. So now the thermodynamics comes into the play. As the ylides is more stabilized, so and again is the steps is, as I mentioned, this is a reversible. So it will going to form the more stable, which is trans. Of course, if you think about these two, in these two carbon where the substitution around these R2 and R1, once they are in the trans, then the interaction, the steric interaction will be less, correct? So this will be a more stable compared to the cis. So because there is a equilibrium here, the equilibrium favors to formation of the more stable one. And once it is going towards the more stable one, now this step is very fast. So that's why once the equilibrium drives towards the trans oxaphosphated intermediate, you will see the formation of the E olefin. So that's why the reaction goes towards formation of the E olefin as a measure in comparison to formation of the corresponding G olefin. As you can see, this is going through a less stable cis oxaphosphated intermediate. Okay. So you can see the one as I mentioned. So this the stabilized ylite formation was discovered by Horner, Warsaw, Demons. So it's called a modified reaction. So they have, now we are going to talk about some of the Wittig reaction variation which are again going to form, starting from a stabilized the phosphorus Wittig. Okay. So here what is going to happen, your stabilized phosphorus ylide going to form. Okay. Again you can see here the difference is, once you are going to form a stabilized ylide, you end up formation of the corresponding E olefin. And again what is happening, instead of alkyl or triaryl phosphine, now you have this phosphonate ylides. So we are moving from the phosphine ylide to a phosphonate ylide here. Okay. Again you have the ester group here and you have a phosphonate ylide here. So that means now you have a phosphonate group there. So it is going to form the stabilized ylide, which is going to form the corresponding E olefin. So in the next slide we are going to talk about some of the reaction where we are forming some sort of a phosphonate ylides. So previously we talked about the formation of, so you start with phosphine and then phosphonium, and from there you form ylide. Now we are talking about phosphonate ylide here, which are again stabilized ylide. You see there are phosphonate group here and you have a ester group, and this proton is getting abstracted to generate an anion here, which is forming a phosphonate ylide. Okay. So phosphonate ylides are more nucleophilic and in less basic than corresponding phosphonium ylide. Okay. As I mentioned before, these corresponding phosphonate ylides will be more nucleophilic, because again once it is more nucleophilic, it is going to react first and going to form the corresponding E olefin through the mechanism I have discussed before. Again, the one of the important thing here, once you have a phosphonate group here, you have a phosphonate group is the electron withdrawing group, you have a ester group. Now this proton in the middle will be much more acidic, so you can use a sodium hydride which can able to abstract this proton and form the corresponding ylide, and from there you can form the corresponding product. Okay. So it is another example of a stabilized ylide. There is a example here, you can see from here they are formation of the corresponding phosphonate ylide going to form using sodium hydride, and that can allow the formation of the olefin between this carbon group and this this carbon. So these two carbon can form a olefin here. Again this is a stabilized one, so you end up forming this olefin, and which can further convert to the antibiotic compound. Now I am going to talk about some of the important modifications. So we talk about that the HWE modification, and we are going to talk about another modification called Steele-Gennady modification or SG modification. So what they have done, I think what was the initial concept, that once you have this type of stabilized ylide, okay, so the Horner's, Warsaw and Immon's modification, where you have learned that once you have this system, once you have this phosphonate ylide, we talk about that, okay, those cases we always get to the corresponding E product. But now the question comes, can you change some of this so that it can end up formation of the G olefin? As I mentioned, one of the advantage of this phosphonol halide is they are more nucleophilic, and this proton can be easily abstracted as I mentioned, because of you have 2 electron withdrawing groups attached with this carbon. So then I think the Steele and Gennady actually introduced first the general way to prepare Z olefins, where they have introduced, the important thing is this the trifluoroethyl group. So instead of this O CH2CH3, they introduce this CF3 group here. So again you can understand, introducing CF3 group means you introduce some sort of electron withdrawing group. This electron withdrawing group play a very important role for the synthesis of corresponding Z olefin, because just by changing this group, what you are bringing, you are changing the selectivity of the corresponding olefin product formation. Of course, you have to use the base, and 18 crown 6 always used to take the sodium or the potassium, and which can now able to generate the corresponding halide here, which can able to react with the aldehyde to form the corresponding Z olefin. We are going to learn the important concept here, that why we are seeing the corresponding Z product here. What is the important thing? They are saying that one of the important thing is electron withdrawing character of the alkoxy group, one of the crucial factor which is affecting the stereoselectivity. Okay. Of course, once you have electron withdrawing group here, the first thing is that you can use this formation of the corresponding, of course you can able to abstract this proton to form the corresponding enolate. Okay. Now the enolate can be able to go for a syn addition or go for anti addition. Means depending on this, if you are adding to the aldehyde, the R2 group can have a steric effect with this phosphorus, with this group. So it will try to go through this anti addition, okay, forming the erythro product instead of the 3O. Okay, so because there is a steric class here. So that's why it is going to go for anti addition. Okay. So once you have anti addition happening to formation of the corresponding erythro product, so you can see this is a Newman projection for this after the addition happen here. Now the next thing is what is happening, there is this oxygen here is going to form a bond with this phosphorus. It is going to attack to the phosphorus and going to form the cis oxaphosphetine intermediate. Now because now this step is a very important step. This is the one important step which is differentiating in compared to the HWE modification. What is happening here? Because there is a phosphorus is attached with a group which is electron withdrawing group, this step is much faster. So again there is some sort of a kinetics playing into the role. Instead of this getting into the equilibrium to equilibrate to the corresponding trans oxaphosphetine, this after the attacking happen, this immediately form this cis oxaphosphetine and going to go to the corresponding Z alkyl, which you have seen in case of unstabilized one. Correct? In case of unstabilized one, we have seen that it is going, the reaction is happening first. It is forming immediately through the kinetic control, formation of the cis oxaphosphetine and going to the product. Here also you are controlling that reactivity by introducing electron withdrawing group in the phosphonate. Okay. And again I think once you have electron withdrawing substitution occupy the apical positions, we stabilize the coordinated oxaphosphetine intermediate, okay, to go to the corresponding Z alkyl. The other important reaction is the Appel reaction, which is again you can able to convert the corresponding secondary primary alcohol to the corresponding alkyl halide using triphenylphosphine, and you can use a CCl4 or CBr4 Br2. There are several different variations of that. Again this is a very important reaction. You can see mechanistically what is happening here. The triphenylphosphine, again see phosphorus is a nucleophile attacking to the carbon tetrachloride, formation of this very important species here, and then you have that at the same time you are generating this species. You guys must have seen there at the beginning when I was talking about the generation of, I think we talk about the alpha elimination when in case of the carbene, but here the alpha elimination is not happening because these two species 1 and 2 forming a tight ion pair. So that's why they after this formation happening, this minus can able to abstract this photon from here, OH photon. Now this O minus can immediately attack to the phosphorus which having the positive charge. Now once you have this species, now this phosphorus actually bound with the oxygen, correct. So once it is bind to the oxygen, it is taking electron density from oxygen. That's now it can act as a leaving group, so the Cl minus can attack here to get rid of this, and it can end up forming a triphenyl phosphine oxide, which is a stable product. Okay. So it is forming from a phosphine, it is going to form a phosphine oxide. Okay. So you can see here it's forming a more stable products here, and it is going from a trivalent to a pentavalent phosphorus. At the same time, it is going to convert the corresponding alcohol to the corresponding alkyl halide. Okay. Okay, there are some of the the variation here. Apple reaction can also effective with the carboxylic acid instead of the alcohol. If you use a carboxylic acid, but it can convert to corresponding oxazolines or thiazolines. Okay, depending on what type of substance. So I think once you have this alcohol, once you have acid here, and after that, what is going to happen? You can remember the acid OH can very similarly alcohol attack to the this species. So this can attack to this species after the formation of the O minus, when this can able to after this proton formation of this. So you can see, you can think about these are very activated ester. So the nucleophile can attack here in the carbonyl. So you have this NH2OH. Once you have this species, it can attack here, form the amide. You have learned about very similar the amide formation, where you take acid, activate with the this type of DCC or EDC to form some sort of activated ester, which get attacked by the amine, form the amide. But you have this OH group there, which can react with another equivalent of this compound. Further, this can attack through this oxygen to get rid of this as a triphenyl phosphine oxide to form this corresponding oxazolines. Okay. And if you have a sulfur here, it can form the corresponding thiazolines. Example here, you have the OH group here converting to the corresponding bromine, and then going to convert to the corresponding natural products. Another important reaction is the Schrodinger reaction, which is a conversion of what you are seeing, you are seeing conversion of azide to the corresponding amine through this very important intermediate. Okay, a phosphoiminium intermediate. We are going to talk about that, and from there you can see formation of the different product. In 1919, the Professor Schrodinger actually and Professor J. Meyer discovered this reaction using the triphenyl phosphine and a phenylazide. Again, I think you can see this is going to first react with the azide, and the triphenyl phosphine react from the phosphazide. Okay, it formed the phosphazide, and then the N2 expulsion happened to form the immunophosphorin or the azylite. Okay, or the immunophosphorus. I think once you have this immunophosphorin, from there once you treat with the water, it is going to form the corresponding amine. If you treat with the corresponding compound like this with a carbonyl group compound, that can form the imidol halide. Okay, or then you have it can form the corresponding imine. Once it attacks to the corresponding carbonyl compound, it can form the imine, or it can form the corresponding amide. Okay, so I think it can form amine, or it can form amide, or it can form a corresponding imine based on the different the reagent you choose. Here you choose acid, here you choose water, here you use corresponding carbonyl compound with a with a Y equal to corresponding, I think it's a acid halide. You use acid halide. Okay, and here you are used corresponding so your Z equal to here oxygen, so you use a carbonyl compound, or if you use a J equal to could be oxygen or sulfur, that can generate the corresponding imidol compound. I am going to talk about the mechanism of this reaction. Again, first thing, the triphenyl phosphine, you can see phosphines are nucleophilic, that can attack here to this nitrogen to form the corresponding phosphazide, correct. Then the phosphazide can attack to the phosphorus and form through this 4-member tangent state. It can form the N2 going to get out, form a immunophosphorin. Once you have immunophosphorin, the water can attack here, and through the proton exchange and the get rid of triphenyl phosphine oxide, it can generate this corresponding amine. The acid can also attack here. Very similarly, the oxygen can attack here, and then you can see it is going to come back and going to form a phosphorus oxygen double bond, and the N minus can attack here first. It's going to come back and then form a corresponding phosphine oxide. So the phosphine oxide is going to get out, and you end up formation of this corresponding amide. Okay. Another application, if you have if you use diphenylphosphine and with carbon disulfide, you end up forming this isothiocyanate, and which can again if you treat with this compound with a amino acid, that can form the corresponding thiohydantoin. So that is another important application of this reaction. Okay. Again, I think the mechanism will be very similar. Formation of this isothiocyanate going to happen by very similar first formation of the iminophosphorant, then it is going to react with the carbon disulfide to form that. Application of this reaction, you can see there is azide here, which finally going to convert to the corresponding amine. Correct. So you can see, let's try to understand how this reaction is through. Okay, first thing is you have a corresponding alcohol here, so that is going to also play important role. After formation of the iminophosphorant, you have this internal alcohol which is going to attack here to the phosphorus. Okay. From here it is going to get rid of triphenylphosphine oxide and form this aziridine, and which can going to get open up to form this very important compound, a very important drug, which is called the Tamiflu. Okay. Again, you can see that there are a couple of important steps here. One is, I think one of the important thing I should mention here, that you can see the amine stereochemistry actually retain here towards the end, but then in this compound, at least in that, the alcohol stereochemistry actually go on for inversion. Why it is happening? Because in this stage, when you are forming this diphenylphosphine oxide bond, this nitrogen attacking here. So there is a SN2 happening here. That's why you see a inversion of the stereochemistry in this particular carbon. So in this part, I talk about the discovery of the phosphorus. I talk about the very important Wittig reaction and its selectivity, the HW modification of this reaction, then Steele-Guenary modification, Appel reaction, and I talk about the Schrodinger reaction from the reduction of azide to amine. Again, these are the textbook. You can able to find most of the things from the Jonathan Clayden books. Again, thank you so much for the coming to the class. I am going to see you guys in the next class. Thank you.